So it's a pleasure to be represented, who I think is known to all of you, but in case he's not, to some, he's from the Indian Institute of Science in Bangalore, where he's National Science Chair and Honorary Professor in the Department of Physics, and he's well known for work on turbulence and condensed matter physics, but also discovered cardiac dynamics, a subject of increasing importance to some of us. And as you may have noticed in last week's workshop, he's been the advisor and educator of several excellent students who participated in our program. But today he's going to talk about something for him rather different, I think, self-gravitating bosonic and axionic systems and a minimal model for pulsar glitches.
Thank you very much, Pat, for the kind introduction, and thank you, Pat and David, for asking me to give this talk. The equations will be similar to some of the equations we've been seeing in the rest of this program. So this is what I will talk about. Let me begin by telling you who's done the work. It started with Vishwanath and Mark. Vishwanath is now in the faculty at the IIT in Kharagpur, and Mark is at the École Normale in Paris. And then another student, Akhilesh, who's now a postdoc in Miami, and Sanjay, who will be graduating soon. And I would like to acknowledge support from all these funding agencies and also the Indo-French Center for Applied Mathematics. So here's an outline of my talk. There are two types of motivation. One is dark matter, the other pulsars. I will give you a brief introduction. And then I will show you that for the problems that I will talk about, the Gross-Pitaevskii-Poisson equations offer a natural way of modeling these systems. And when we get to pulsars, we will also include a crust. The work will be based after we define the models on direct numerical simulations and then results and conclusions. So let me tell you things that all of you must know well. Dark matter has a very rich history. It is a beautiful article in Reviews of Modern Physics, which lays out this history. It goes back at least as far as Kelvin, who talked about dark bodies, and Poincaré, who talked about matière obscure. And the first person who put it on a somewhat more firm footing was Zwicky, who used the virial theorem to infer the existence of unseen dark matter, which he called Dunkel Materie. Then, of course, there are the celebrated measurements of Rubin and Ford. What were those measurements? Those measurements are summarized in this slide, which I have taken from this paper. Now, if you look at the rotation velocity of galaxies, then these are the measured values. And if you just said what would follow from the laws of mechanics, given what's inside, you would get that curve. So you really need to add this bit. And then the general consensus is that that's from dark matter in the halo, all right? So that's the macroscopic evidence for dark matter. Now, needless to say, if it exists, then it plays a central role in our understanding of modern cosmology. And the general numbers that are given are that 85% of the matter in the universe, matter, not energy, is non-baryonic cold dark matter, all right? But identifying the nature of this dark matter remains one of the primary open questions. There are any number of excellent experiments, but they have not been able to settle the issue. Okay, so here is various statements you will find in fairly recent reviews and so on. I mean, dark matter searches have expanded in their diversity and are becoming a driving force behind many observations, but there is still no new smoking gun. All right, in the old days, people used to talk about baryonic dark matter, compact objects, but not very luminous. These were then called massive astrophysical compact halo objects, or MACHOs for short. I mean, they like acronyms. Then, of course, there's another suggestion completely orthogonal to dark matter that goes back to Milgram in 1982, just modified Newtonian dynamics. You change 1/r² at sufficiently large scales. So that has continued, but the general consensus, if I talk to my colleagues in astrophysics, they say, no, it's really dark matter. So after MACHOs came WIMPs, weakly interacting massive particles. These were the strongest candidates for dark matter, but the best experiment so far, it's just not been found yet. What are the other possibilities? One other possibility is the axion. This was introduced in particle physics to solve the so-called strong CP problem. CP is preserved in QCD. So one of the suggestions due to Brachet and Quinn was that this could be overcome by introducing a new global U1 symmetry that is spontaneously broken. And of course, it was realized by, Wilczek and Weinberg soon thereafter that, of course, the moment you break this global symmetry, you will get a so-called Nambu-Goldstone boson, which they call the axion. And this axion shows up in many modern series of particles and so on. Furthermore, there could be bosonic objects. So while our colleagues in the dark matter community keep on, perfecting their measurements and so on, it is at least useful to see what we can do. If we have such dark matter candidates, can we study models where they, might occur? Furthermore, our study will also lead us to a minimal model for pulsars and their glitches, which I will explain as I go along. So let me remind you quickly, what is a pulsar? Well, it's a neutron star with a huge magnetic field, and the beam of radiation goes out this way, and it sort of rotates at a, very high frequency. And when the beam hits us, it's sort of like a lighthouse. That's when we see the beam. But what's inside the neutron star, most important for us, is this crust, to which I will return in the modeling, and the outer core, which consists of proton flux tubes in a superconducting state and neutron vortices for a superfluid. It was realized quite early in 1959 by A.B. Migdal that the densities are such that even though the temperature is very high, the matter inside these objects must be in either a superfluid or superconducting state, right? So I'll come back to that later. So let me first begin with the formation of compact objects at finite temperatures in one of the dark matter candidates, namely a self-gravitating bosonic system. Okay, so I'm going to work basically with variants of this equation. So let me go over this first slide carefully. If there were no gravity, the top equation is the Gross-Pitaevskii-Equation, which we would use to describe a weakly interacting Bose gas. So this is what we would describe for a superfluid. You can worry about weak interactions later, but let's not go in there yet. The strength of the interactions is measured by little g. M is the mass of the bosons. That's the number density. That's the complex wave function, which describes the Bose gas. And now, if we add gravity, we'll have another term here where phi is the gravitational potential, which must then satisfy the Poisson equation. So that's, comes from the number density of the bosons, okay? And that mean has to be taken off. And as you will see soon, that will lead to the celebrated Jeans instability. Now, in the absence of gravity, that is this capital G equal to 0, there will be a sound speed because the superfluid, if you write it in hydrodynamic way, is compressible, has a compressible part. So there's speed of sound. And then there's a coherence length, which sets the scale of the core, the radius of the core of the quantum vortices. Now, how do we study such things? I'll say this only once. I mean, the pseudospectral methods, which we know well from hydrodynamical studies, okay? And in 3D, Kristolovich and Brachet, they studied this, and then later Shukla, Brachet, and I in 2 dimensions. So whenever you carry out a pseudospectral simulation, perforce you truncate the number of modes. You can't have an infinite number of Fourier modes. Nobody can. So when you do that, that we refer to as spectral truncation or Galerkin truncation. Now, if you were a statistical mechanician, you would say, aha, but this is sort of like a canonical evolution. Energy is conserved. So eventually the system must thermalize. By the time the system thermalizes completely, you are not solving the partial differential equation that you set out to solve. But there is a sufficient range where you still have spectral accuracy and the beginnings of thermalization so that you can define a temperature, as I will show you in the context of these calculations. And when you have such a temperature, you can come up with cleverer ways of getting to the equilibrium state, which I will define as we go along. So for example, here in an old paper, we looked at turbulence in the 2-dimensional Fourier-truncated Gross-Pitaevskii equation, okay, which you would for a 2-dimensional superfluid, let us say. And to make a long story short, I have just listed what happens in this system if you carry out a good enough calculation. There are 4 regimes. There are initial transients that depend on initial conditions. Then there is onset of thermalization. The energy and occupation number spectra begin to show power law scaling, okay? And eventually there is partial thermalization where the spectra show clear power laws, which begin to show thermalization. And if you go all the way, you might not think that you would be able to uncover this, but at least the statistical mechanicians will realize that there should be a Berezinski-Kostless-Thouless transition in 2 dimensions, and you can uncover it completely by using such a study. Okay, so I'm not going to talk about all that today. I'm going to talk about Gross-Pitaevskii-Poisson. So back to Gross-Pitaevskii-Poisson. I have reinstated the gravity, so you will see capital G there. And if you linearize this Gross-Pitaevskii-Poisson around the constant wave function mod psi squared is n0, you will obtain the following dispersion relation. I hope I've got all my signs right. And this displays a low k Jeans instability, which says that for wave numbers less than this Jeans wave number, you will get collapse, okay? And this is what Jeans first did in the case of a cluster of gas. Now, again, we're going to use this, the Fourier-truncated Gross-Pitaevskii. So I put it in here. And for the case, for the experts, we have put in the way in which we Fourier truncate. So all Fourier modes beyond some k max, we're going to set equal to 0. So that's the equation we're going to solve. Now, if you do things right, your numeric should conserve the number of particles, the total energy, and the momentum with suitable de-aliasing. And the energy is normally broken up into the so-called quantum part, the interaction part. This little g is the strength of the interaction between bosons, and then capital G is the gravitational part. So again, excuse me, as in the pure Gross-Pitaevskii. Here again, you will get a finite temperature effect in this Gross-Pitaevskii-Poisson equation. And again, for the statistical mechanicians in the audience, if you want to study equilibration all the way, it's better not to work in the microcanonical ensemble, but it's better to go to the grand canonical. So you can do that here by going to imaginary time and writing down the associated stochastic Ginzburg-Landau-Poisson equation, which has some external noise. This is just like in Gross-Pitaevskii, but with imaginary time. And then you have a chemical potential to control the total number of particles. You have temperature, and this noise is Gaussian, and so on. As I will show you, this is, at a practical level, this is just a way of getting to the equilibrium state in an efficient way. That's all. It's not very profound, and the evolution in this imaginary time has no physical meaning. Yes? It's white noise, zero mean Gaussian. Okay, right. Yes, right. It's exactly, going from one ensemble to the others. No different. Okay, so now let's try to study the gravitational collapse in the system. We begin with an initial wave function, the uniform density, and we put a little perturbation on it, okay? And as I will show you, we get a collapse. Before I show you that, I should tell you that at zero temperature and with various approximations, Chavanis has been studying this system for a long time. And if you ignore the thermal fluctuations and you write down the energy of the collapsed object, assuming that it is a sphere, and let us say you use the so-called Thomas Fermi limit where there's a vanishing quantum error energy contribution, then you will get this radius. So there are various such results for the energy and so on, semi-analytical, against which we can compare our results. Excuse me, but we will go well beyond that. To monitor the radius of the collapsed object, we will just use the radius of gyration, which we can get from the density distribution that we have. Okay, we can, I can go through non-dimensionalized units later, whoever's interested, but we can non-dimensionalize all lengths, etc., and so on. We do many, many runs with lots of different resolutions, some with the stochastic Ginzburg-Landau-Poisson that I told you about, and others with the Gross-Pitaevskii-Poisson. Okay, and for real dynamics, we really have to do Gross-Pitaevskii. So here is the initial condition, and let's see how it collapses. This is in stochastic Ginzburg-Landau-Poisson, and that's a sphere with periodic boundary conditions. Okay, so it just collapses to that state. Now, when it collapses, you can ask what is the radius doing, and the radius goes eventually to a constant value, and the gravitational energy also goes to some value. All right. Now you can ask, would your Gross-Pitaevskii have done the same thing? And indeed it would have, but this will be at some finite temperature, so more fluctuations. Okay, but this is what it will look like. All right. So if I plot the same plot for, excuse me, the radius versus time, you see it will be oscillatory, and I will show you that eventually it will reach the same value which the stochastic Ginzburg-Landau-Poisson did. So that's why the other one is faster. This is the plot of the energy. Okay, so I will not show you every detail, but it's also possible that you start with so much energy that the system does not collapse. Okay, it's just shredded apart, too many fluctuations. So both possibilities exist, and you know, sorry, this one. Where did am I going the right way? Yes. So this one is supposed to show you, I think, that if I compare with the previous one, that Gross-Pitaevskii and SGLE actually go to the same value. So it's a good way of helping the numerics along. This is nothing very profound here. It's just a good way of handling the numerics. Yeah. Well, I mean, at the moment, we do it a very low-level way. We do n cubed and we do 2n whole cubed, and if the results don't agree, then we just refine more. Yes, if you go back to the approximate theories that Chavanis, etc., have done, then you could have some feeling for the radius given those parameter values. As you have surmised correctly, there are many parameters. So you could use those analytical arguments, which are really at zero temperature, to get an estimate. Okay, but yes. Yes.
Stronger than linear theory about collapse and the radius of gyration. I mean, what brings this to mind is the superficial similarity of this story to Langmuir collapse.
Okay.
In 3 dimensions.
All right. So
rigorously what the final state.
Okay, my feeling is that for the full thing at finite temperature, there's nothing rigorous. But zero temperature, there are these Thomas Fermi type approximations which Chavanis has done. So I think that's the nearest to analytical work. Okay, let me skip over some of these. Right. Now, if you do these sorts of calculations carefully and you plot it versus this temperature, which I've told you how to get out, then the scaled energy of the object goes like this. That's kinetic, interaction, gravitational total. And there seems to be some sort of a jump. The jump is more visible in a plot of the radius versus this temperature. And indeed, if you talk like a statistical mechanician, really there is a first-order transition, which I have shown here by plotting the scale radius versus the temperature. Red is what we would call a heating run as you increase the temperature. But when you cool, you follow the green curve and only then collapse, leading to significant hysteresis. So this is a clear signature of a first-order transition, all right? Distinct from the continuous Bose-Einstein condensation, which you would have without gravity, which would be continuous. Okay, the states that go with this transition are shown here. Now, you can ask, is that all you can do? How about binaries? Can you do binaries? And don't look at the details, but we can pick initial conditions so that you get a binary. So these are bosonic stars, and they form a binary system, and they go around each other. And whether they collapse into each other or not depends on parameters. For this particular simulation, on the time scale of the simulation, it did not collapse. Okay, so this whole framework has a lot of structure in it, and we can see how far we can push it. So let me pause at this stage. This is just Gross-Pitaevskii-Poisson. And we have presented a first principles computational study that takes into account thermal effects of a superfluid, which is self-gravitating. And we go well beyond earlier theories, which use Thomas Fermi. And, we get a first-order transition, which is, as I said, distinctly different from the conventional Bose-Einstein condensation, all right? And we can also get rotating binaries. So why should we even think about axions? Now, another very good article in Reviews of Modern Physics by Bratton and Zhang say that the particle that makes up the dark matter of the universe could be an axion or an axion-like particle. So just like our collection of bosons condensed, axions should be able to condense into a bound Bose-Einstein condensate, which they would call an axion star. And it is possible that a significant fraction of the axion matter is in the form of axion stars. But those who do the calculations at the field theory or whatever level, they conclude that the scattering length A, I didn't spend enough time on the scattering length, but the scattering length is related directly to the strength of the interaction between the bosons. So for axions, this scattering length is negative. Therefore, the axions attract. Of course, you have gravitational attraction. If these are also attracting, they will, of course, collapse. So how do we study an axionic condensate? So this is what we did next in this paper. So, of course, the only way to control it is to put in the next higher order term. This is what we would do in critical phenomena, you know, when the coefficient of the phi to the 4 term becomes negative, we put in the phi to the 6 term, which is important if you're studying, let us say, tricritical points. So here at the level of the energy, you would put in a psi to the 6 term, which at the level of the equations of motion would be a quintic term. So if you want to study axionic condensates, you have to study the cubic quintic Gross-Pitaevskii-Poisson equation. All right? So again, this you know well. The only term I've added is here. That's Poisson. Excuse me. So these will be the conserved quantities. In the absence of gravity, speed of sound will get changed a bit. The coherence length will get changed a bit, but we can all compute all these things. And again, we will study this cubic quintic Gross-Pitaevskii-Poisson by using the pseudospectral method, Galerkin-truncated, and all these objects should be this is the energy, etc. Which we, of course.
Excuse me, what's
yes.
the sign in G2?
G2 is positive, stabilizing, of course. Otherwise, not only would a mathematician get upset, your code would blow up okay, very quickly. It would, you know. So that's what's controlling the size of the object for fixed all other things. So if you want to study finite temperature effects, again, you use the same trick. You go to stochastic cubic quintic. It becomes a mouthful. Okay, but you know what I mean. And there is this noise term, again, Gaussian, etc. Yes. No. This is just to get it to converge to the equilibrium of that. No Bose-Einstein, nothing. This is just a trick. This is how we would do grand canonical ensemble in statistical mechanics.
Satisfy the fluctuations coefficient here.
Yes, it does. You see the coefficient here, everything. It's cooked up to satisfy all that. That's why it equilibrates. Okay, so there's no problem. Now, so far, I have not added rotation. I could have in the previous example, but I didn't. So let me now add it. I mean, as all of you know well, if you take a Bose-Einstein condensate and you rotate it rapidly, it'll get threaded by vortices. So this should happen even if there is dark matter and there's a galactic halo, it should be there. It should be there in the stars. But so far, it's not in our equations. So if you go through all that I have said, you would have to add a term like this at the level of the stochastic Ginzburg-Landau-Poisson. Lz is the z component of the angular momentum, and that is the rotation frequency. Okay, So first, let me show you the hysteresis in this case. I'm showing you the hysteresis at 0 temperature. I am changing the system by holding all other interactions fixed, but just increasing the strength of the gravitational attraction. So at very low gravitational attraction, the system is disordered. But then, at least to our surprise, it goes through the following steps. It first organizes itself into sheets, and then cylinders, and finally the sphere. This is how it collapses at a practical level in the calculation. We were then very gratified to see that people like Zeldovich had talked about, what do they call it? Pancakes. So these are referred to as Zeldovich pancakes. Okay, these are the pancakes of our simulation. And there was also talk in some of these astrophysics papers, not with detailed calculations, of cosmological hysteresis. Now, of course, I'm not an astrophysicist, but perhaps this is cosmological hysteresis. I don't know. Okay, but this is the hysteresis in our model. Now, you can tune through these loops by changing the interaction strength of the axions. There again, you get these 3 loops. And you can do it by changing the temperature. Then also you get, but then the loops are not as distinct and they're not as pronounced. Okay, now let me show you for the first time what happens when we rotate this condensed object. So this is a collapsed axionic star. In some units, everything is non-dimensionalized. I'll be happy to talk of units later if someone's interested. If it is below some critical frequency omega sub c, there is no vortex. Then vortices appear, and then more vortices appear. And you can actually plot omega c, the critical frequency, as a function of the interaction strength between axions, and it falls as G2 increases. And in any practical calculation, this is how the vortices appear. First, nothing, and then they start puncturing the condensate. And I think this is the result for this case, right? So that's nice. The collapsed object is doing what it is supposed to do, that when you spin it fast enough, you get... Now, can we get binaries? The answer is yes. Of course, because you have more things, you can get more complicated things. So here is an initial condition with the centers of masses separated by a distance d and these different velocities. So they start off with some relative angular momentum. You can also put in a phase. And when you do it, you get these nice things. You can already see the movies running. They don't collapse right away, but they come, they sort of bounce off each other. And precisely how it happens, it won't surprise any of the mathematicians in the audience. It depends on initial conditions and it depends on parameters. Okay? But we have full numerical control over such things. Here is the thing on units. I didn't want to get into it because it's a morass. But if you put in, you can say, what does your simulation box mean? Well, then you have to figure out axion masses. And so if you were trying to aim at dark matter halos, then you would have a box which is 2 pi whole cubed kiloparsecs cubed. And these time steps would be 4.8 years. If you were just talking of an axionic star, compact object, we are talking of kilometers cubed and microseconds. So, okay, here's again a good time to take stock. So this is the first principle study of the first time I've seen at least, of the collapse of an axionic object at finite temperature. Again, Chavanis had done some calculations at 0 temperature within the Thomas Fermi approximation. And we have shown that with this truncated cubic quintic Gross-Pitaevskii-Poisson equation, we can begin to study axionic compact objects, and they can show two hysteresis loops, and we can also get rotating binary axion stars. Okay, now this will look like a change of gear. It's a minor change of gear. You will see that I will use the same equations as we go along. In 1969, in that issue of Nature, two important papers were published. The first by these two, Radhakrishnan and Manchester, and the other by Reichley and Downs. They observed, I mean, I showed you this picture of this pulsar going around very rapidly. And by good measurements, one in Australia, the other in the United States, they found that the period suddenly falls. It's going up like this and bang, goes down, bang, you know? And these came to be known as pulsar glitches. And many, many years later, we're talking 2018 now, Manchester said that this was the first glitch was 1969, and by 2018, there were examples of about 520 glitches and about 180 pulsars. Okay. So where do they, this way. So what's happening? Soon after superconductivity was discovered, A.B. Migdal made the important observation that in objects like neutron stars, which are highly compactified, even though you might think that the temperature is very high, because of the enormous density, the temperature is below what would be the superfluid temperature for the superfluid part and the superconducting temperature for the superconducting part. So first, let's look at the dominant component. Apparently, neutrons constitute about 95% of such neutron stars or pulsars. And given the conditions there, they form Cooper pairs, which eventually form a superfluid. So it has been suggested first, I think, in the old days, 1969 or 70, soon after the discovery of glitches by Bain, Pethick, and Pines, that these glitches might be occurring because of interactions between superconducting vortices and the crust of the pulsar. That's the claim. And then this group has sort of pushed that. They suggested that the zeroth order theory could use the two-dimensional Gross-Pitaevskii-Poisson for the superfluid part, put in a crust, but they didn't want to deal with gravity, so they put in a quadratic confining potential. Okay? And then they did something in 3 dimensions too. But of course, I mean, gravitational effects are crucial, so we then put in our minimal self-gravitating model for this system, but in addition, we added a crust. Furthermore, we must have rotation because we need the vortices in the superfluid. Okay? So in this paper then, we put in, let me give you the results first so that you have you know where we are going. In the absence of the crust potential, we show that if we rotate such a bosonic star as I've shown you for the axionic case, the star is threaded by vortices. The interactions of these vortices with the crust potential yields what people in self-organized criticality might call stick-slip dynamics and dynamical glitches. These will show up in the angular momentum that is transferred to the crust from the bosonic star. I will show you what that means. So we will analyze the, sorry, you have a question? No, you have a question? No. So we will analyze the time series of the crust angular momentum, and we will show that there will be lots of fluctuations. And the statistics of the fluctuations will have signatures of self-organized criticality, one second, which has also been reported in the measurements. Yes. No, for 1 second, 1 minute. Next slide. Sorry. So here is good old Gross-Pitaevskii-Poisson, which all of you know well by now. I have now added the crust potential. Okay. And because this is a minimal model, I will say that this crust potential depends on only one angle theta. I know that's a great simplification. The crust is actually, people worry about what sort of crystal do we have in the crust. No, we're not going to do all that. Given that there is a crust potential, then if IC is the moment of inertia of the crust, that's how it evolves. Plus we put in a friction term. Okay, so the gross simplification, there's only one angle. Then here's the crust potential. The crust has a favored radius r crust, but which has a certain thickness delta r crust. And for a point at Rp, and then there is a periodic part. What is this periodic part that is there? It's to give you pinning sites, which will pin the vortices. I mean, this is well known to people who do superconductors and, you know, Kim and Anderson and things like that. But let's not go there now. And N crust determines the number of pinning sites, etc. I mean, there's some cleverness here in the way in which we define this, but this is a numerical detail for the moment. So let's not worry too much about this. The important thing to note is that the crust acts on the Gross-Pitaevskii-Poisson superfluid just as the superfluid acts on the crust. And it's all there in the equations. And again, by now you know all this, pseudospectral, Fourier-truncated. And in the absence of the crust potential, the momentum is conserved, etc. These are the conserved quantities. We can write them down. Again, to get to the equilibrium case, which was missed by other people, it really helps to use this little side track through the stochastic Ginzburg-Landau-Poisson version of this problem. Okay, but that's, just think of that as a numerical scheme. Okay. No, crust does, no? I mean, V theta is evolving. I mean, yeah. So theta is evolving. So it's not quenched also, to answer your question. It's not, I mean, some people do quenched, so it's a good question. I mean, the Newcastle group does quenched. Yes, it was completely quenched. You are absolutely right. Any condensed matter physicist will recognize that, but it's not quenched. Yeah.
How time scales of that?
Okay, let me save that for the last slide. Okay, if you start doing time scales, then we are in big trouble. Okay, we'll get there. All right, so we also want to put in rotation and all that. So let's not go into all the details. But just like we put in rotation into the axionic case, we can put in rotation. Now, here is a plot of the z component of the angular momentum versus time. There's some slow decay. That's because a cubic lattice is not exactly spherically symmetric, but we can, you know, fix that with suitable things. But if you increase omega, you go along this red curve, and then you have vortices threading it, and then you come back this way. So again, there's something hysteretic. And when the vortices go through this collapsed object, that's what you have. This is without the crust. Now you put in the crust. The crust is in blue. The vortices are showing up in red. And as time progresses, okay, I'll show you a movie later, these things can go out of the assembly. And when they go out, there's a complicated time series here. So let me just plot over here I can identify the crust angular momentum scaled suitably versus time non-dimensionalized. That's a complicated time series. If you blow it up, it's still complicated. So clearly, we need to analyze this by some statistical means. And this is what is done. This is what the astronomers were doing. We see, first of all, that the crust can either lose or gain angular momentum to or from the superfluid because the vortices stick or slip from the crust. That mathematics we've already built into the model at the simplest level. And to characterize the properties of these stick-slip events, we calculate the gain delta JC in the crust angular momentum between successive minima and maxima of JC. And we call delta JC the event size. Then there is an event duration, TED, which is the time difference between successive minima and maxima of JC. And then there is a waiting time, the time difference between two successive maxima. So this is what the astronomers do. We're just doing exactly what they do. Now, of course, these fluctuate, so you need probability distribution functions. And it is more useful if you want to get power laws to look at the cumulative or complementary cumulative PDFs. So here is the event size PDF, cumulative, versus see, this is a log-log plot. Straight line means a power law. Again, this is the event duration PDF. Straight line means a power law. And this one is a semi-log plot. Straight line means an exponential decay. The first point to note is this is qualitatively exactly what the astronomers see. Okay? That these two PDFs are power law. Yes? Well, nothing, no, and they probably depend on parameters, but we were very gratified to note that the power law that we get is actually seen in some pulsars. I should also say that they don't have as long time series as we do. We have a simplified model, we can get a much longer time series. Okay, but it's not like orders of magnitude off. I mean, we are delighted, And so, okay. All right. Okay, now, last bit of my talk. I will not keep you beyond noon, don't worry. The first time I gave this talk, my good astronomer colleague came and said, there's huge magnetic fields in pulsars. Where's your magnetic field? Okay, so that took a couple of years, and we have just put this preprint out on the arXiv. So now we're going to, I told you the neutrons are 95%. The remaining 5% are protons. The neutrons form superfluid vortices. The protons form flux tubes. Okay? All right, so if you really have to do this right, unfortunately, this is what you have to do. All the Gross-Pitaevskii-Poisson stuff is there for the neutron superfluid. For the condensed matter people in the audience, this is nice because this is, a superconductor in a magnetic field. This is what we would do for a type 2 superconductor. D sub A is this minimal coupling thing here. Okay, so I have a magnetic field which is hiding in A, and I have a wave function for the protons at this level. Okay, Q is 2e, that's the Cooper pairs. Gross-Pitaevskii, I'm not even showing you. Poisson is sitting there also. And then, of course, there's vector potential. There's Maxwell. Okay, so there's the full electromagnetic Lagrangian. Other people who had done this had some static approximation, but we don't do anything static. Everything is all there. And then there is interaction between the neutron Cooper pairs and the proton Cooper pairs. So psi n, psi p. both density and current interactions. Okay. So Sanjay is a really brave graduate student. He did the whole calculation. Let me not try to summarize all his results, but let me show you some time evolution here. So in these plots, the neutron vortices are shown in red, and the proton flux tubes are shown in this light blue color. And in this particular run, the rotation axis is there, and then this develops a magnetic moment. I'm not going through every detail, which has an angle chi with this rotation axis. And if you plot the cosine of this chi versus time, lo and behold, you get what the geodynamo people would love, reversals. Okay? I mean, of course, these have never been seen, but you know, it might be just a question of time scales. But there are reversals in the real-time dynamics of this complicated object. There is also interaction between the crust, which is the same color code, the outer blue is the crust. And now we have neutron vortices in red and proton flux tubes in blue. And there are more neutron vortices in this initial thing. So they're the ones. We start with 12, only 6 are left. But their expulsion from this collapsed object is somewhat hindered by the presence of the proton flux tubes because of the interactions that we have put in. Okay? But at the end of the day, you plot the crust angular momentum versus time, complicated, you blow up this, you get that, you blow up that, you get that, you blow up that, you get that. Anyone who's looked at fractal things will say, obviously something scaling here. And indeed, there is self-organized criticality by using the same complementary PDS that I told you about. Paolo for the event sizes and event durations, and exponential for the waiting time. So we've been able to do many, many things. Let me just pause a little bit to remind you what we've been able to do. I'm sorry? Sure. Simple way, meaning, of course, there is the London moment is generated dynamically. So that's nice. I mean, I don't think anyone had shown in this context the development of a London moment. And the freezing in is basically dynamical version. Suppose you just looked at the proton system. This is what Abrikosov got the Nobel for, the flux phase. You get the flux phase. So just like when we rotated the object, we got vortices threading it. When there's a magnetic field above some level, then there are flux tubes that go through. And now we've put everything in, they interact. It's really... Well, not completely, because we're spinning it around. They're all interacting, but they're there. Yes, you're right. I mean, if we turned off everything, if we had only that, they would order. No problem. But here it's all... Okay. So we have been able to obtain a precise characterization of the entrainment of these proton superconducting flux tubes around these neutrons. I mean, I haven't shown you everything. Yeah? Okay, we can put in direct interactions and so on. Let me not... But so first thing is, it's sort of gratifying that we are still getting exponents which are in the right ballpark. But when we write down minimal models, we should always pause at the end and say, how minimal is it? So let me remind you some numbers for a typical neutron star. The radius is 10 kilometers. We have our simulation box. And the core sizes of neutron-superfluid vortices, sorry, I got this number completely wrong. It's 10 to the minus 15, not 10 to the 15. Huh? So there's a long way to go. I mean, there's no way any simulation will resolve all those scales. Then there is the ratio of the speed of light to the speed of sound. It's with these parameters is 10 to the 6. There's no way Any simulation will get that. But having said that, at least, we are pleasantly surprised that such a simple model can get so many things qualitatively right and quantitatively not entirely wrong, in the sense that the exponent is in the right ballpark. So with that, let me thank you, and I'll be happy to answer any questions you have.
All right. Questions? People?
Yes.
Okay. In the crust, there can be another phenomenon which is called pyromagnetic effect.
Mhm.
Symmetry between right-handed and left-handed terminals,
Mhm.
and results appearance of additional electric current and the duration of problem. So this effect by alluded to your model.
Okay, I have to go back and do my homework. It's obviously not here, but let me see whether it is at all feasible to put it in. Okay, thank you for the suggestion. Okay, good.
What's next on your agenda?
For this, well, let's pause a little bit, because I think we've come a reasonable way. Of course, we could do bigger and better, but we still have to see whether there are important physical effects that are left out. There's also some element of, some people say the pinning centers are frozen. I mean, like Christina was implying, that they are quenched, they don't evolve. So should we put those in? We have to see. I think there's a lot to, and also talk to the astronomers and astrophysicists and see what they have to suggest. Yeah.
So you talk about
Yes. Mm-hmm. No, I know. I've done whole image too. Okay, good.
that field.
I don't know. I don't know, because first of all, from this, I mean, whole MHD would be an effective hydrodynamical description, which we would have to abstract from all this. At the moment, I'm not sure how to do that, because whole MHD certainly will have no superfluid, no superconductor. It just has just the ion inertial scale thrown in addition to. Don't know. I need to look it up. Thank you for asking that question. Yes. Well, I don't know what your definition of explain is. Meaning, there's the old Yang thing. I do it with paper and pencil. So I don't have an explanation, but yeah, I appreciate your question. Then it comes out with the numerics. It's a complicated time series. We use the same sort of analysis that the astronomers do. So I don't know, I mean, to the extent that we can't understand every detail of our numerics, we don't have an explanation. But, oh yes, those are all real plots from our simulations. Okay. Yes.
So I'm looking at the
Mm-hmm. Yeah, red ones are neutron vortices, if I remember correctly, and the blue ones are the proton flux tubes, proton superconductor flux tubes. Yeah, well, there is the lattice. The blue stuff is a lattice. That's the crust potential. So there is the crust potential also, which is giving the lattice. No, no, no. This is the lattice of the crust.
That is
Yeah, so there is a third entity. Okay.